Okay, so hello everyone, and you're all very welcome back to another webinar brought to you by nQuery from Dotmatics. This month, we're going to be looking at intervals, so sample size for frequentist and Bayesian statistical intervals. In particular, we'll be discussing the design considerations for confidence intervals, prediction and tolerance intervals, and credible intervals. As always, I'd like to thank everyone for showing the interest by registering for this webinar, and I hope you find the session worthwhile. Before we get started, I'll just deal with a few quick frequently asked questions. So to start, this webinar is being recorded, and a copy of the recording and the slides will be sent to you shortly after the session is finished, hopefully within 24 hours. If you're experiencing any technical difficulties, let us know in the chat and we'll do our best to help out. And then finally, you can also use the chat function for any questions relating to the content, and then they'll be answered either at the end if there's time, or else we'll respond by email after the session is finished. Just to introduce myself, my name is Paul Murphy, and I'm an nQuery research statistician here at StatSolves. I mostly work on table development across all areas of nQuery, and I'll be your host for today. So here's just a quick overview of what I'm going to be talking about. So we'll be starting off with a broad overview of statistical intervals, what types exist and what they're used for. Then I'll be going into more detail on confidence intervals, prediction intervals, tolerance intervals, and then finally Bayesian credible intervals. We'll also be looking into which scenarios each of these are useful in and how sample size procedures work and look like for these intervals. Like what parameters are likely to be required compared to, say, a typical equivalent power calculation. I'll be including lots of practical examples in this session, and the sample size calculations will be demonstrated using these worked examples. All of these calculations will be conducted using nQuery, the complete solution for optimizing your clinical trial designs. Here at nQuery, we have many solutions for fixed-term, Bayesian, and adaptive designs, from preclinical research all the way through to post-marketing. nQuery is a very well-established and widely used and recognized software. It's been around for over 25 years and has more than 50,000 users in over 100 countries. It's currently available in 4 tiers, Base being mostly fixed-term designs, Plus being Bayesian, Pro being adaptive, and then finally Expert being for milestone predictions. And the files that I'll be creating in this demonstration will be made available alongside the slides after the webinar. So if you'd like to explore these for yourself and you're not already a user, I'll have information about how you can easily access a fully featured free trial of the software at the end of the demonstration. Okay. So that's the housekeeping taken care of. And without further ado, let's start off with a brief introduction to statistical intervals. So starting out, I guess the most basic question to address here is, what is an interval in a statistical context? So essentially, we're looking to specify a range of likely or plausible values for a parameter. So at least in a two-sided case, this range or interval would be defined by a lower and an upper limit. This parameter of interest could be something like a mean, a proportion, an effect size, or a nuisance parameter like a standard deviation. And instead of simply using a point estimate for this parameter, we also want an indication of the precision or the quality of the estimate by specifying likely upper and lower bounds. How likely? Well, that's something we'll talk about in a moment. So like you could say that a narrow interval would tend to suggest that a particular point estimate is of higher quality or more precise because you'd have fewer plausible values in the smaller range. whereas a wider interval would indicate less precision. But like I said, we'll see a bit later that it's not always quite that easy to interpret, especially in the frequentist case. But as a starting point, I think it's usually broadly true. One quick side note I'll make first is that in a one-sided case, you'll either have an upper or a lower limit, and then some natural bound on the other side. So this natural bound could be plus or minus infinity if the parameter was something like a mean, or 0 or 1 if the parameter was a proportion. So then tying this into sample sizes, you would expect that most statistical intervals will become more precise, i.e. narrower, as the sample size increases. One explanation for this is because increasing the sample size will decrease the standard error. And as we'll see throughout the webinar, standard error is a quantity that shows up quite a lot in many of these interval width calculations. And then reducing this standard error narrows the overall interval width. In some cases, as the sample size tends to infinity, the interval will converge on the point estimate, but this isn't always the case. Sometimes the upper and lower intervals have other limiting values that they'll converge towards as n approaches infinity, and these values aren't necessarily going to be the point estimate. So now the question you might be asking is, why would a trialist need to think about this? And well, if we're saying that the interval width is an indicator of quality or of precision, then often a sponsor or regulator will have a target or a maximum acceptable interval width in mind. So then you would need to determine, say, the minimum sample size required to achieve this target interval width. Okay, so in practice, you're probably most likely to encounter or use frequentist intervals. And within the frequentist interval space, you're most likely to encounter a confidence interval. And what all of these frequentist intervals have in common is that they're procedures based on repeated sampling. So like for example, you generate a very large number of intervals using the same procedure, and then you calculate the percentage that contain the true value of the parameter you're interested in. So think of it this way. If you wanted a 95% confidence interval for a mean, then you might sample from the same population a very large number of times, say 100,000, generate this interval each time using the same procedure, and 95,000 of them would contain the true mean. I know I'm getting into the weeds a little early here, but I think it's very important to say from the outset that you can't make any inferences about any individual iteration from this procedure. All you can say is that the confidence interval was generated from a procedure where, under repeated sampling, X%, or often 95%, of such intervals would contain the true value. In contrast to this somewhat awkward interpretation, Bayesian intervals can offer a much more attractive and intuitive interpretation, but we'll get onto that in the second half of the webinar. But first, let's step back a bit and take a look at different types of common statistical intervals. I think we'll have time to touch on 4 today. The first 3 are frequentists, so we have confidence intervals, prediction intervals, and tolerance intervals, and then finally Bayesian credible intervals. So for the 3 frequentist intervals, we're saying that under repeated sampling, we want X% of the generated intervals to contain something. And then what that something is depends on the type of interval we're using. Up to now, what I've basically been describing as confidence intervals, where you want to contain a parameter like mean, standard deviation, or proportion. Like you might want to be sure that a certain percentage of total intervals under repeated sampling contain a true mean. Next, looking at prediction intervals. With these, your concern is the probability of a future sample being included in the interval, hence the prediction aspect. So the most common case you'll come across here is looking at a single individual future iteration. Like, what is the probability that the next additional measurement from the same population is contained within this interval? Again, this is under repeated sampling. Another type of prediction interval could be the mean or standard deviation of various or multiple future samples also. But as I said, the single future iteration is the most common use. And then finally, on the frequentist side, tolerance intervals are used when you want an interval to contain a specified proportion of the sample itself and also a proportion of any future samples taken from that population. So say, instead of wanting a mean to be in your interval, like with a confidence interval, you're now looking for an interval containing a certain proportion, say 75% of the population, with a certain pre-specified probability. And then last, but certainly not least, we have Bayesian credible intervals, where this time you want your interval to contain the true parameter with a given probability. In other words, the interval contains a specified proportion of the posterior. And I'll be giving a little bit of background on the Bayesian framework and in particular the posterior when I introduce this topic in more detail a little bit later. But for now, so we know that there are various types of intervals, many more than the four I've just mentioned, but what are some things that you should be considering when choosing your interval? Well, that really depends on what you want to do. Like, if the target of the interval is a parameter, like a mean or a standard deviation, then you'll more than likely be constructing a confidence interval. If it's an interval to contain future observations, then it would be a prediction interval. Or if you wanted an interval containing a certain proportion of all means, then you'd have a tolerance interval. You might also want to ask yourself if you're happy or comfortable with this frequentist repeated sampling approach, or would you prefer to use Bayesian methods, in which case you'd be looking at a credible interval. The nature of the underlying population and sampling procedure is also an important practical consideration. Like, for a prediction interval, are you sure that the distribution of the population will remain the same across all times? And then finally, there's the practical question of how will you construct the interval once you're given the data? Confidence intervals usually use parametric models, like a confidence interval for a mean would use the Z statistic multiplied by the standard error. However, tolerance intervals often use non-parametric distribution-free methods. And just to say that many of the more complex intervals are often derived via bootstrapping these days. So it's another sort of empirical, non-parametric approach. And that's become much more popular recently, given how easy it is, or relatively easy at least, to run simulations nowadays. Right, so now let's start getting into a little bit more detail. And so because confidence intervals are the most widely used statistical interval and are probably the area that most of you will have the most familiarity with, we'll start here. So I just have a couple of slides and then we'll get on to some practical examples. So confidence intervals are clearly very widely used and they're often like one of the first things you'd come across in introductory statistics courses. But I feel like they're often misunderstood and misinterpreted. A lot of this could be down to the fact that their interpretation isn't actually particularly intuitive. So like I've said in the previous slide, a confidence interval is constructed so that under repeated sampling, Certain percentage of intervals, say 95%, will include a parameter of interest, these parameters being means, proportions, standard deviations, etc. And this does not mean that any individual interval has a certain probability of containing this parameter. And I think that's a very important distinction. There's a very interesting 2016 paper by Morey et al. That's in the references at the end. It's called The Fallacy of Placing Confidence in Confidence Intervals. And here the authors outline some very interesting situations where the confidence interval ends up being quite unsatisfactory, to be honest. Nevertheless, they are very commonly used, especially still in the area of clinical trials. And to be honest, in many real-world applications, they are considered to still be adequate. Also, they do tend to have some nice features, like where confidence intervals can correspond to certain statistical tests. And then you'd say like that if the confidence interval doesn't contain 0, it would be equivalent to observing a p-value less than the alpha value of the confidence level. So for example, your two-sided significance level of 0.025 corresponding to a 95% confidence interval. This is used explicitly in equivalence testing, where you check if the confidence interval is contained entirely within the equivalence bound. And again, it always helps because the confidence intervals are so common and well established. Sample size methods are available for almost all common endpoints like means, proportions, survival, crossover, correlation, coefficients, etc. Right, so in terms of sample size for confidence intervals, if we assume the parametric case, then the sample size methods will often be based on a classic normal approximation or some other classic parametric model. Like, for example, here on the right, we have the confidence interval formula for one normally distributed mean. So the confidence interval is the sample mean pi bar plus or minus Z alpha multiplied by the standard error. So for 95% two-sided interval, this Z alpha would be the famous 1.96. And here, the standard error is the standard deviation sigma divided by the square root of n. And then in a simple case like this, you can easily just rearrange the formula to have n on the left-hand side on its own. And in this case, the confidence interval is symmetric, so omega is equal to half of the confidence interval width. And similar normal approximations like this one exist for endpoints such as proportions or survival, and these are still the most commonly used formulas. But it is worth noting that exact methods are also available for many common cases. And an important point here is that these sample size calculations are targeting the average precision of an interval. In other words, an average confidence interval width. Just one quick sidebar here, actually. I'm saying width, but the size of a confidence interval is also often described as the length, which can be a bit confusing, both words being used to describe the same thing, but I'm going to try to stick to width. So obviously here, a narrow or a small width is considered more precise, whereas a wider or larger confidence interval width would be considered less precise or of lower quality. When you see the words average precision, you'd expect that intuitively, if you have a targeted confidence interval width, then 50% of the time, the actual width would be wider, and 50% of the time it would be narrower than this. But in reality, through real world examples, it's been shown, at least in cases like one mean, that the actual achieved width will be slightly less than the stated or targeted width more than 50% of the time. However, the likelihood is that the achieved width will still be very close to the target width. And it's really only in cases where you really do need your achieved width to be smaller than or equal to the target that you might consider some other options. And Copper and Hafner provide a solution, or at least something to help you with this, by incorporating the coverage probability. So here you can state a specific probability that the interval will be no greater than the stated or target interval length. For example, you could say that you need 80% probability that the actual confidence interval length is less than or equal to, say, 1. And one last point before an example. If you consider the upper and lower confidence interval limits as random variables, which is the case in the frequentist paradigm, then there's a direct comparison with a power calculation if you assume that there's no location dependence in the variance. And we'll be demonstrating this in a few moments too. Okay, so let's move on to an example of a sample size determination for a confidence interval. So this is a very small study with 2 means, probably an early phase trial. It was for rosiglitazone for insulin sensitivity. They measured the difference in glucose disposal rates, and a sample size of 10 per group was required for a 95% confidence interval that had a half width of 1.5 milligrams per kilograms per minute when the standard deviation was 1.7. So you'll notice that we're using half width here, which just makes things a little bit tidier when the interval is symmetric. Right, so let's take a look at how we'd approach this sample size determination in the software. Right, so for anyone who hasn't seen it before, this is the nQuery home screen. So to open a table or a procedure, you'd just click New, or you go File, New, and then you'd use either the buttons or the search feature to find your test. But I've already opened all of the tables that we'll be using for our work examples today. All of the nQuery procedures follow this spreadsheet-like input-output format, where each row corresponds to a parameter where you can enter a value. The rows in yellow are the quantities that can be solved for, so in this case, omega and n. And if we had any gray rows, then they'd indicate that the quantity is read-only. Then each column represents a separate independent calculation. So for example, here, if I fill from confidence level down to standard deviation, and then enter one of omega or n, nQuery will automatically calculate the other. Each table has what's called a home card, giving a description of the method that will be used and the references. And then each row has its own individual health card, which again gives an introduction along with some suggested values and acceptable entries. So let's just replicate the original trial here. We want a 95% confidence interval, so the confidence level is 0.95. It's two-sided, the standard deviation was 1.7. So now we want to specify the distance from the mean to the limit. In other words, this is the half width of the symmetric confidence interval. And our target here was 1.5 milligrams per kilograms per minute, I think it was measured in. And you see nQuery automatically calculates a sample size per group of 10, which agrees with the summary on the last slide. If we want to explore the scenario a bit further, or maybe do a little sensitivity analysis, you can go to the plot user selected rows up here. And what we'll do is we'll see what effect changing the standard deviation has on the confidence interval half width. So sigma goes on the x-axis, omega on the y. Our standard deviation estimate was 1.7. So let's vary this from, let's say 1 to 2 in steps of 0.05. Click OK. And you see we get a linear relationship. If the standard deviation is 1, then the half width is quite narrow at 0.877. But when the standard deviation was larger, indicating less precision, the confidence interval width was wider. The half width here, 1.753. Let's also plot the sample size per group against the half-width. So this time n will go on the x-axis, and we'll vary it for, just use a default 2 to 200 in steps of 10. And then, as expected, we see as the confidence interval narrows or the width decreases, the sample size increases. So hopefully you can see how easy it is to get started with a sample size calculation. As you recall from the last couple of slides, we were saying that this means that a group sample size of 10 is targeting an average width of 1.5, which suggests that 50% of the time it could be slightly below 1.5 or slightly above for the other 50%. Given how you wouldn't really expect this to vary too much, this basic calculation might be sufficient in a lot of cases. But like I was getting at earlier, what if for some reason you're in a situation where you really don't want to have an interval wider than 1.5? Then you could use the next table here, which has the Cupper and Hafner coverage probability included. So this allows you to set a target probability for how likely you are to achieve an interval smaller than the target. So let's say we want 80% probability, or 0.8, that the actual interval is less than the target. So enter that coverage probability, and the rest of the table is the same. So it's 95% confidence, two-sided, a standard deviation of 1.7, and a half-width of 1.5. And now we get a slight increase of 14 per group. So that's the requirement to achieve this increased coverage probability. If, say, we upped the coverage to 99%, you see the sample size per group would rise again to 18%, or to 18 per group, excuse me. Now, before we move on to another example, I said I'd just show you how this confidence interval procedure is related to a power calculation for a test like the two sample Z test. So I'm just going to open some notes that I've prepared in the tab here. And I've rearranged the sample size formula for the confidence interval to get the half-width omega on its own. So just note, if you're comparing this to the formula I had in the slides, just going back a bit here, this n here is the total sample size, as opposed to sample size per group, which nQuery uses. So for the demonstration, I've divided that by 2, just if there's any confusion. So back to nQuery. Then for equal variances and equal group sample sizes, the standard error, denoted S, can be calculated as follows in terms of the common standard deviation and the sample size per group. So that's very straightforward. And this allows you to express the width in terms of the standardized Z statistic for the significance level and the standard error. I've highlighted that in green. Then the definition of the Z statistic for this two means test is the difference in means, denoted delta, divided by the standard error. So putting that all together, you can get an expression for delta in terms of the confidence interval half-width, the standardized Z statistic for the power, and the standard error, the other green here. And in our example, we'll be using, again, a standard deviation of 1.7, sample size per group of 10, which gives a standard error of 0.7602. The confidence interval half-width was 1.5, and we're going to target 80% power. So here the Z beta is 0.8416. If it was 95% power, it would be 1.96. From here, we can calculate the corresponding difference in means, delta, as 2.1398. So let's just confirm all of that in the table now. So we have alpha 0.05, two-sided, delta 2.1398, common standard deviations of 1.7, and a sample size per group of 10. And there you go, we see that the 80% power is confirmed. So I hope this has helped to demonstrate how these two procedures can be intrinsically linked. So this was the two means case, but I also just want to briefly show you a one proportion example. So this was a trial for a combination of therapies for a pancreatic disease. They constructed a confidence interval for the proportion responding positively to the treatment. Again, it was two-sided 95% with a half-width of 0.2. The standard or expected proportion was 0.5 and the required sample size was 24. This expected proportion of 0.5 is very conservative, like it's straight down the middle. And so a proportion of a half is going to give you the greatest variance, hence the widest or least precise confidence interval. So in other words, you're picking the worst case scenario here. So let's go back into the software again and open the proportions table. So the first thing you'll probably notice is that the requirements for this are very, very similar to the means case. So we can get straight into it, entering the confidence level of 95%. The expected proportion was 0.5, and this time we'll say that our required sample size was 24. And this calculates the half-width of 0.2, or if you look into the actual value, it was slightly larger than 0.2. Again, as you can see in the title, this used a normal approximation, but other calculation methods are available if required. So it's in another table here. So for example, we have the option to choose between simple asymptotic method, which is basically the same as the normal approximation, and the Wilson score method, both with and without a continuity correction, or you can use a Klopper-Pearson exact method. And that's what we'll do now. Let's see what sample size would have been required for this same width, but this time using the exact method. So we'll stick to the same confidence level, expected proportion of 0.5, Klopper-Pearson, and now it's asking for the full width as opposed to the half width. So twice 0.2 is 0.4. And we see that a sample size of 27 is required to achieve a width that's just a little bit narrower than the target. So like in this case, if n equals 28 would have given a width just higher than the target. Or excuse me, n equals 26 would have given a width just higher than the target. So like as expected, this exact method requires a slightly larger sample size. And just to say as well, the reason why we're using the full width here as opposed to a half width is because using some of these methods, the interval isn't necessarily going to be symmetric. So the upper and lower limits are also given explicitly in the read-only columns here at the end. I'll just say we also have confidence interval procedures for parameters like correlation coefficients, AUC, or area under the curve, for receiver operating characteristics, hazard ratios, and most of the regression parameters. But for now, let's move on to prediction and tolerance intervals. Okay, so while confidence intervals were concerned with containing a particular parameter, prediction intervals are concerned with containing a future parameter value or a future sample with a given degree of confidence. The most commonly cited case is a prediction interval for one future iteration or one future sample. Like we've created an interval and now we want to take one additional measurement and the value should be within that interval with a given degree of confidence. For example, let's say we take 50 people and construct a prediction interval. If this was a 95% prediction interval, then out of the next 1,000 we sample, we want 950 of these to be contained within the interval. Then we also have tolerance intervals. Now, these will try to contain a specific proportion of the population under repeated sampling, as opposed to a confidence interval which tried to contain a specific parameter. So, for example, you might require an interval to contain 80% of the population, 95% of the time, under repeated sampling. And also, you can actually reimagine this in terms of a confidence interval for the percentile of the upper and lower confidence limits. Like the 80% proportion I just mentioned would be, in a two-sided case, would be equivalent to the 10th and 90th percentile, and now you'd want to have confidence intervals for those. So now we'll get into the considerations for sample size determinations. For prediction intervals, the theory is relatively well developed, especially for the one normal mean case. I'll just say as well as this, nQuery also offers sample size procedures for future standard deviation and for k simultaneous future observations. Now, while these methods for confidence intervals, while the methods for confidence intervals looked quite similar to power calculations, they use concepts like standard error, the prediction interval calculations are a little bit more abstract. Here, the sample size will be calculated relative to what's known as a limiting interval. And the definitions of these limiting intervals for future mean, k future observations, and standard deviation are all here on the right. The real implication here is that as n tends to infinity, the width of the interval will converge to these limits here. Unlike what is often the case in the confidence intervals, the width won't approach 0. And the same concept also applies to tolerance intervals. Like, even if you knew the exact distribution perfectly beforehand, then the tolerance interval would still, by definition, it would have to be a certain width because it would still have to include a specific proportion of the total sample. So there is a hard limit here, and it can't get infinitesimally small. For both of these, the sample size here is the sample size that will be used to generate the interval, and the future sample size, usually denoted k, is assumed to be a known fixed value. So the classic prediction interval case, the one we'll be looking at in an example in a moment, predicting one future value. Here k equals 1. And also this k equals 1 case is the same interval for one future mean. In terms of tolerance intervals, nQuery covers the one normal, one exponential, and one gamma cases. And there's also a non-parametric approach to this that we don't currently offer in nQuery, but it's something we're definitely going to look into including in a future update. How do these tolerance calculations work? So the calculations we have in nQuery follow the Gunter's approach. So in these cases, we'll be focusing on the proportion covered as opposed to things like means and standard deviations. And then we can imply what this proportion is going to be based on the distribution. You also have the option to incorporate the idea of a coverage probability by specifying what's called an exceedance margin. For an example of how this works, let's say you need at least 80% coverage probability, and now you can add in an additional constraint that say you will have 85% coverage with a probability of at least X. These tolerance intervals, they're often used in areas like manufacturing or maybe devices, where you might require that, say, 80% of components must have a mean lifespan between X and Y years with this probability. So let's keep going and move on to some more examples. So this is a real-world prediction interval example for pediatric range for cortisol. The sample size was 160, and that was made up of 60 males and 60 females. And this was expected to achieve a 95% prediction interval with a width 1.2% larger than that of the smallest achievable prediction interval. And then if you took each gender group separately, the 95% prediction interval for each was expected to have a width 2.5% larger. So let's see how we'd implement this in nQuery now. So as you can see here, the table is quite different to the confidence level one, and some of the required inputs are a bit more abstract. If you take a look at the home card as well, you'll notice that the input requirements are slightly different or slightly like non-standard for this table. So if you want to calculate the expected relative width, which is what we're looking for, then the upper prediction bound and the exceedance probability rows are both to be left blank. So let's start with a confidence level of 0.95, and we're only considering one future sample, so k equals 1. And the total sample size to create the prediction interval is 120. And here, this gives an expected relative width of 1.012. In other words, that's 1.2% larger than that of the smallest achievable prediction interval, which is what was stated. Now, let's do the same thing with the gender groups, which were, they had a sample size of 60 each. And this time, the expected relative width was 1.025, a 2.5% increase, again matching what we saw in the previous slide. This so-called smallest achievable prediction interval, or the limiting interval that everything is relative to, this can be explicitly calculated using the formula I showed a few slides back. So it's like this formula, but as you can see, this would require the standard deviation, which we don't have in this example. You might also be wondering, how would you use the upper prediction bound and exceedance probability rows? So instead of targeting the expected relative width, instead we can say that we want it to be above a certain bound, WU, with a stated exceedance probability. So let's try and say we have an exceedance probability of 0.5, or half the time. So enter in our, stick to the same confidence level, two-sided, an exceedance probability of 0.5. And then keep the same future and sample size. And then we see we get an upper prediction bound that's very similar, not exactly the same, but very, very similar to the expected relative width. So we're saying here that, like, on average, the prediction bound is 1.012, like 50% of the time we're above it, 50% of the time we're below it, which is basically the same concept as the expected relative width. So that was a prediction interval, but moving on, I'll just do one very quick tolerance interval example. So this is kind of an example from the original Gunter textbook. So it's kind of out of context and more just a theoretical example. It's a one exponential case, and this time we're looking for a one-sided 95% tolerance interval. We want to cover a proportion of 90% and have an exceedance margin of an additional 5% with an exceedance probability of 5%. And for this, a sample size of 22 was required. So I'll show you that table in nQuery. So this is the tolerance interval for exponential. And again, you can see it's quite straightforward to complete, actually. Confidence level of 0.95. So we want 90% of the population, or a proportion of 0.9, covered within this interval. In addition to this, we want an exceedance margin of 0.05. So as well as covering the 90%, we want an upper bound of 95% for the sample coverage. So in the one-sided case, we'll just add on the 5 to the 90 to get 95%. And then the probability that the coverage exceeds this upper bound is 5%. So 0.05 again here. And we see that we get the sample size of 22, which agrees with the Gunter reference. And we also outputted in the read-only row as a tolerance factor. And this is it's sort of an equivalent to the standard error that you'd see in a confidence interval calculation. So these were all frequentist intervals, but for the rest of the session, I want to talk about Bayesian statistical intervals. And in particular, I'll be focusing on credible intervals. Okay, so we don't have too much time to dwell on the whole Bayesian context, but I did include this because I felt it always needs some background. So just very, very briefly, essentially, Bayesian analysis is used to combine existing knowledge, expert opinion, and real-world data to make inferences. This can be done because under the Bayesian interpretation of probability, you express a prior degree of belief in a hypothesis or an event, and then this belief can change as new information becomes available. So this allows us to use the evidence as it accumulates. Our model parameters are considered to be random variables, and we want to estimate what's known as the posterior distribution of the parameter of interest. So then the relationship between the prior, the posterior, and the data are all underpinned by Bayes' theorem here on the right. So we have a probability of theta given d. This is the posterior distribution of a parameter theta, given or having observed the data. The probability of d given theta is the likelihood of getting the observed data given this value of the parameter theta. That's multiplied by the prior, which is our prior distribution of the parameter before observing any data. This is the subjective part, I guess. And that's all multiplied by the marginal probability of the data or the evidence. I'm going to keep going and move on, but if you'd like more detail on this, just get in touch and we can easily send you some resources. But in terms of statistical intervals, the most commonly used Bayesian method for interval estimation is, of course, the credible interval. This can be considered as the Bayesian alternative to the frequentist confidence interval. Like I said before, confidence intervals are often misinterpreted in statements such as like a 95% confidence interval means that there's a 95% probability that the true value is in this interval. Whereas as we've learned, the actual interpretation would be that if you repeated the process, constructed a very large number of intervals in the same way, then 95% of them would contain the true parameter value. This doesn't tell you anything about the probability of any individual confidence interval containing the parameter. And that is why credible intervals can become a very appealing alternative, because along with the ability to incorporate prior knowledge, which is, part of the whole Bayesian framework, provided your assumptions are met, like your prior is properly specified, etc., then a credible interval can be interpreted as a probability that the true value is in the interval. So for a 95% credible interval, it is correct to say that there's a 95% probability that the true value is in this interval. On a more technical level, what's actually happening is that You're going to specify a coverage error as opposed to a significance level. So that would be 2.5% two-sided or 5% one-sided. And you construct the credible interval so that it contains 95% of the posterior probability distribution. So that's the posterior of the parameter of interest. So this is after you have your prior knowledge and your data. And just another important difference to reiterate is that under the Bayesian framework, your parameters are random variables and your bounds are fixed, whereas under the frequentist paradigm, it's the opposite. The bounds are random variables and the parameters are fixed. And one unfortunate consequence of the bounds being random variables under the frequentist interpretation is that if they're incorrect, there's no bound on how wrong they could theoretically be. So avoiding this potential issue might be another reason to consider a credible interval instead. So now we're going to move on to how you would construct a credible interval and the sample size determination methods that govern them. This follows methods by Adcock in 1988 and Joseph and Bellesley in 1997. And these involve the testing of normal means and incorporate uncertainty into the variance estimate. So you use prior information about the expected mean and about the precision. So here the precision is just 1 over the variance. When it comes to interval construction and sample size determination for that, the process is a little bit more complicated than with confidence intervals. We'll look at 3 selection criteria for sample size and 3 testing scenarios based on what type of prior information is available or what type of final analysis you want to conduct. So our 3 selection criteria are the average coverage criterion, or ACC, average length criterion, or ALC, and worst outcome criterion, WOC. So I'm going to take a little bit of time just to distinguish between these. Let's start with average coverage. Here, the length of the credible interval is fixed. Say we chose 0.1, and it ensures that on average, the coverage of the posterior probability is at least what you stated it is. So that's often 95%. So you specify your 5% coverage error, length 0.1. Now this length is fixed at 0.1, and on average, the coverage probability is at least 95%. This was the method that was originally proposed by Adcock, and then the average length criterion was introduced by Joseph and Bellesley, and it's basically the inverse of the average coverage. So this time you fix the coverage, say at 95%, and then on average, the length of your interval will be at most your set value. So say specify 5% coverage error, again length 0.1. This time it's the coverage that's fixed at 95%, and now on average the length will be at most 0.1. Then finally there's the worst outcome criterion, or WOC. This is an extension of the average length, but average length criterion, but it allows you to be more confident than saying just on average. So like with the average length criterion, there's still a 50% chance that the actual length will be slightly larger than your specified value. So that's something a similar thing we've come across throughout this webinar. Now you can select a cutoff, say like 80%, and then for a fixed coverage, maybe 95%, the probability that the length is at most what you say it is 80%. So this can be looked at in a very similar way to the coverage probability adjustment in confidence intervals, which was the second means table that I showed you in the demonstration. For more information on these criteria, just you can see the Joseph and Bellesley paper, and there'll be a link to that in the references at the end. In terms of the methodologies, you have the known precision case, which is a relatively trivial extension of the frequentist scenario. You just sort of subtract the size of the prior that was used to find this known precision from the sample size. Much more interestingly is the unknown precision. This is where you must specify a prior distribution. And then finally, there's a different type of interval called a mixed Bayesian likelihood or mixed Bayesian frequentist interval. This is a very interesting approach where you want credible interval characteristics, but you'll still be using a confidence interval in the final analysis. So here you fulfill both the Bayesian criteria of the interval containing 95% of the posterior probability, and you get the nice intuitive interpretation that goes with that, but you also meet the frequentist criteria that if you were to construct many such intervals under repeated sampling, 95% of them would contain the true value. This is useful for those who ultimately need to use a confidence interval for regulatory purposes or higher, just you need to use a confidence interval, but you still want to enjoy the benefits of Bayesian properties. So this is an example of one normal mean that comes from the original 1997 Joseph and Bellisday paper. And we're going to use nQuery to replicate example 2 in the table here. So we're going to use a gamma distribution with shape and rate parameters of 2 as the prior distribution of the precision. There's a hyperparameter of n0 of 10, which is basically your prior sample size, or the size of the study that was used to obtain this information about the mean and the precision. The interval length is 0.2, so that's the length of our credible or mixed Bayesian likelihood interval, and the coverage probability is 0.95. We're given a sample size for the frequentist confidence interval, which is 385, and then we have sample sizes for credible intervals under the 3 criteria, and the corresponding sample size for a mixed Bayesian likelihood interval under the same 3 criteria. Just note that the 95% attached to the worst outcome criterion here just means that the probability that the actual length is less than or equal to the stated length for a fixed coverage is 95%. Right, so for the final time, let's go back to nQuery. And this is the credible interval table for unknown precision. I'll begin by choosing the average coverage criterion from the drop-down list. The coverage error is 1 minus the coverage probability, so it's 0.05. So this is the probability that the true mean is outside the interval. So this is the Bayesian interpretation. Nu and beta are the gamma shape and rate parameters for the prior distribution of the precision. So again, the precision is just 1 over the variance, and we said that it was going to be 2, 2. So in a gamma distribution, the mean is nu over beta and the variance is nu over beta squared. So if the parameters are the same, you get a mean of 1 and the variance will decrease as the parameters increase. So here with our 2, 2, we have mean 1 and variance half. So that's quite wide and not very informative. So this suggests that we're not too confident about our precision estimate. The interval length of the credible interval is 0.2, and the hyperparameter, or our prior sample size, is 10. It's quite small, and you'd expect the required sample size to decrease as this increases. The subset is only required for worst outcome criterion, so we should get our sample size now, of 761. I'll repeat this for average length, and again for worst outcome. So the default subset for worst outcome criterion is 0.05, just means that the probability that the length is greater than 0.2, given coverage probability of 95% is just 5%. And now we see that the average coverage and average length sample sizes are somewhat similar. These can vary as to which is larger depending on the coverage error or the interval length requirements. But clearly, and as expected, the worst outcome criterion stands out as having the largest sample size. This is because it has the most strict conditions attached to it, especially when there's just only a 5% chance that the achieved interval length will be larger than the stated length. If we increase the gamma parameters, it means we'll be expressing more confidence in our prior precision estimate, so you'd expect the sample size to decrease. So example, if we go 10-10, the sample size decreases to 426, or for very large values like 1,000, you get 375. So at this point, you're very confident about the precision estimate, and it becomes quite close to the frequentist confidence interval case. So let's actually look at that table here. It's very easy to complete. 0.95. The standard deviation is 1 because our two gamma parameters were the same. And we're back to using half widths here. So half of 0.2 is 0.1. And this gives 385, which is just 375 plus the hyperparameter of 10. So it is interesting that the average coverage criterion with fixed length is very similar to the confidence interval with fixed coverage if you have a very informative prior. And now finally, the mixed Bayesian likelihood implementation, it's very similar to the credible interval. So I've just pre-filled some of the table here to speed things up a bit. We no longer are using a hyperparameter because it's a frequentist analysis we're going to be conducting now. So we're not making any inferences based on the prior anymore. This method uses a simulation, so you can specify a seed if you want to replicate the calculation, and I'll just enter the number of simulations, and the calculations should run. So it's a slight sample size increase compared to the credible interval calculation, but it's not too different because our hyperparameter was quite small to begin with earlier. Just note here that these values differ slightly from the ones given in the table, and that's just down to the seed and number of simulations used. A criticism of these methods is that you can see that the average coverage and average length can return quite different values. Like, okay, it's obvious why worst outcome will be much higher, but it can be quite, it mightn't be obvious which of the other two to choose between. And basically, your decision will depend on what you're most concerned about getting correct, the length or the coverage. Now, I'm aware we're pretty much out of time, but one thing I was going to mention, so I'll just briefly fly through it here. One of the biggest barriers to using a Bayesian method can be the question of where you get your prior from. So this is a method also developed by Joseph and Bellesley that incorporates information from two different sources. They use an example of an optimistic and a pessimistic prior. So you state two different priors using beta parameters here. And then you want the highest posterior density intervals derived from both of the priors to agree within a pre-specified amount. And this is known as the Bayesian consensus-based approach. So I don't have time to go into details, but I have just pre-filled an example here. So you have three criteria: average coverage, worst outcome, and a modified worst outcome. And then for two of the criteria, you need to select what's called, or specify what's called a design prior. And this is what will be used to derive the set of all possible data. So it can be a linear combination of the two priors above. You can specify a third prior to reflect an average opinion, which is called a clinical prior, or you can require that both priors will work. Okay, so I just wanted to make you aware that this approach exists, and if you'd like more information or a detailed example, then please do get in touch. But unfortunately, we are out of time now, so I'll just quickly wrap up. So today we discussed how to use different types of statistical intervals to help give insight into the uncertainty of our estimates. We spent some time exploring confidence intervals as they're the most common type, but also looked at other frequentist intervals such as tolerance and prediction. And then finally, we switched to the Bayesian perspective and examined credible intervals as an alternative to the confidence interval. At this point, I'd like to thank you all for attending. And if anyone would like to try a 14-day free trial of the fully featured expert tier of nQuery, Just go to statsols.com/nQuery-trial, and all we require from you is an email address, and you'll get a browser-based version. If you have any questions from either today or just in general, send us an email at info@statsols.com, and we'll get back to you as soon as possible. So once again, thank you for your time, thank you for your interest, and goodbye.